Okay, we're now going to have a look at the ozone layer and the significance of these halogen compounds. So first things first, what is the ozone layer? It's a layer found in the outer stratosphere, and it's quite important to us humans because it absorbs harmful radiation from the sun. So it absorbs stuff like ultraviolet radiation, or to be more precise, it's UVB, that is harmful to humans, so it can cause mutation in our cells. So that's why the ozone layer is of significance to us. And you may have seen that the ozone layer is depleting for various reasons, which I will go into in a little bit. So first things first, what do we mean by the ozone? So ozone is a gas and it has the formula O3. Okay, so this is ozone. And naturally, the ozone is in equilibrium with oxygen. So naturally, in the stratosphere, we have this equilibrium set up between oxygen and ozone. And as I said, this is a natural equilibrium, and what it does is it ensures that we always have enough ozone present. So we have oxygen reacting with an oxygen radical. We don't tend to draw that radical in to form ozone, and then the reverse happens as well. And if we allow this to just happen naturally, that's absolutely fine. That means there's always going to be ozone present. But man-made things have been affecting this equilibrium here, and they've been pushing the equilibrium in this direction, in the reverse direction. And that's causing the depletion of ozone faster than we're expecting. So let's discuss the reason behind this equilibrium being disturbed. And the reason behind that are organohalogen compounds. So organohalogen compounds essentially just means organic compounds with a halogen present in them. Okay, so we've looked at examples of that. So haloalkanes are technically organohalogens. So anywhere where you've got any sort of carbon chain with a halogen, that's classed as organohalogen, just as kind of like a name for all those types of molecules. So one example of organohalogens are something called CFCs. Okay, and CFCs essentially mean chlorofluorocarbons. Okay, so they're organic compounds that contain both chlorine and fluorine. And this is what we tend to use in refrigerators, we tend to use in solvents, and it's not usually an issue when it's in the atmosphere. Okay, so these tend to be quite stable compounds because we've got strong carbon halogen bonds. So in the atmosphere, not an issue whatsoever. The issue is when these CFCs reach towards the ozone layer, so the outer stratosphere. The reason being is because when they get to the outer stratosphere, they have UV light present. Okay, so if you remember, UV light can be used to create homolytic fission. Okay, so we've looked at homolytic fission where we had halogens, and in the presence of UV light, they will undergo homolytic fission and form radicals. And that is what happens when the CFCs reach the outer stratosphere. So one example of a CFC is this compound here. Okay, so it's a chlorofluorocarbon. It's got carbon, fluorine, and chlorine in there. Okay, so when this molecule is in our atmosphere, not a problem. Okay, these bonds are very strong, they don't break. When it reaches the outer stratosphere and UV light is present, so in the presence of UV light, that can cause bonds to break homolytically. Okay, and over here we've got two types of bonds. We've got a CF bond and we've got a CCl bond. Now, so these two, if you remember, the CCl bond's bond enthalpy is less. Okay, so the CF bond is very strong. The CCl bond is strong, but it's weaker than the CF. So that means this CCl bond will break, and it will break homolytically. And when it does that, it's going to form a radical here, and it's going to form a chlorine radical as well. Okay, these chlorine radicals are awful when it comes to the ozone layer, and I'm going to show you why. So this step over here, this is called the initiation step. So remember, the initiation step is where we form radicals via homolytic fission. If you want to, I've drawn these out. If you wanted to write these out, like that, it's under UV, that forms CCl2. So there's a radical here, and it forms a radical like that. Okay, so once this chlorine radical is formed, this is going to react in the with the ozone layer. Okay, so this step here is just the same thing twice, but this step here is the initiation step. So let's now have a look at the propagation. So if you remember, this is a radical reaction. So we've got initiation, propagation, and termination. So let's now have a look at the propagation steps. Okay, so we've got our chlorine radical. That chlorine radical reacts with the ozone. Okay, and what that does, the chlorine radical plucks off an oxygen. So that then forms ClO radical, and because it's plucked off an oxygen, we've left with O2. This chlorine radical, this chlorine oxygen radical reacts in the next propagation step, and it reacts with, so if you remember, we have a natural equilibrium set up between oxygen and ozone. It reacts with the oxygen here, and that reforms the chlorine radical, and it forms O2. This chlorine radical that is reformed in the second propagation step, this is now ready to do the same thing again. And this chlorine radical is going to, do this many, many times. So one chlorine radical can react with many, many ozone molecules. Okay. And obviously there's then a termination step. So termination could literally be any two of these radicals reacting together to terminate the reaction. But hopefully you can see that overall, in terms of what's reacted, so if we ignore the chlorine radicals, so if we ignore all the radicals, overall we've got O3 that's reacted with oxygen. So we've got O3 and O that have been the reactants. And in terms of our products, we have formed 2O2. Okay, so overall, chlorine radicals cause this. Okay, and this is the equation that is disrupting that natural equilibrium between oxygen and ozone. So chlorine will convert ozone into oxygen. Okay, and this is what is causing the depletion of the ozone layer due to these CFCs. Right, it's not just chlorine radicals that do this. It is also nitrogen oxide radicals. Now, nitrogen oxide radicals are formed from lightning, so they're natural. They're naturally formed. There's nothing we can do about that. But these nitrogen oxide radicals, again, in terms of the propagation step, or propagation steps, sorry, these also in the same way react with ozone to break it down. So that's going to form, so it's going to pluck off an oxygen here. So that's going to form NO2 radical plus O2. And then that radical is going to react with an oxygen, and that's going to reform the NO radical and O2. So again, ignoring all the radicals, overall we've had O3 react with O to form 2O2. So again, nitrogen oxide radicals are causing depletion of the ozone layer. But again, this one here is natural. There's nothing we can really do to control this one, whereas CFCs are something that are man-made. We are the ones that are making them and releasing them into the atmosphere.